it's been rather curious where this whole singular value decomposition thing comes from and where these odd definitions might originate from. So recall that the singular value decomposition for non-square matrices or square matrices, but typically we want to use this for m by n matrices with rank r greater than 0. So this just means that the A matrix is not all columns of zeros. If it is, this method will not apply directly. U is an m by m matrix with orthonormal columns. Sigma contains along its diagonals the sigma i's, and capital V transpose is an n by n matrix such that V has orthonormal columns. And we defined things as follows. We first of all started with the formation of the A transpose A matrix, which what we know is if you multiply the transpose of a matrix by itself, you get an n by n symmetric matrix. And that is really key here. We get an n by n matrix. Since A is m by n, this is n by m. A is m by n, so the multiplication there will yield an n by n matrix, and we've already proven that this matrix will be symmetric. We said define the sigma i's to be the square root of the lambda i's for the A transpose A. The capital V matrix consists of the eigenvectors of that A transpose A matrix. So Vi is an eigenvector of A transpose A. And then we said, let's form this bizarre U matrix that is going to be consisting of these columns that are functions of each of the eigenvectors, A, Vi divided by sigma I. So first of all, one thing that we should point out here is that if in fact it is the case for symmetric matrices, which we know from a theorem that it is, that the eigenvectors will be orthogonal, and then we normalize them by dividing each of the vectors by their magnitude, then any function, any linear combination of those eigenvectors will also be orthogonal. And so that's why we can say U is orthonormal. Well, at least it's orthogonal because it's going to be a linear combination of the orthogonal eigenvectors Vi. And we can show this. We can show that these are all going to be orthogonal. Again, these are all orthogonal. And in fact, orthonormal because we're going to normalize them. That's something that we have to do. So by virtue of n by n symmetric matrices, these will be orthogonal. We'll normalize them. And now if we know that the dot product between any two of the eigenvectors is going to be 0. So if we were to look at, say, well, what about P1 times P dotted with P2? Dotted with P2, for example, is that going to equal 0? Well, we can try it out. We know that this is equal to A V1 divided by sigma 1. Now this is going to be a transpose because even though the dot product is defined in such a way for vectors where when we dot two vectors together, it's assumed that one of them is a transpose, but we often don't write that transpose there. So a vector transposed with itself, in this case AV2 over sigma 2, we just want to see that this is going to be equal to 0. So first of all, the sigmas I can factor out, sigma 1, sigma 2, because of the fact they're scalars. So now the transpose of AV1 will be V1 transpose times A transpose. And now from the second factor here, I have AV2. Okay, well, I already know V1 and V2 are orthogonal, but what do I know about A transpose A times V2? Well, A transpose A times V2 is equal to lambda 2 V2. And the reason this is the case is when we studied eigenvalues and eigenvectors, we studied this equation here. Now, lambda and v, if this was lambda 1 and v1, or lambda 2 and v2, then v2 and lambda 2 were an eigenvalue eigenvector pair of A. But our A in this case is the matrix A transpose A. So that itself is a matrix, and v2 is an eigenvector of A transpose A, and lambda 2 is an eigenvalue of A transpose A. So what this leaves me with is 1 over sigma 1 sigma 2, and since this is equal to v1 transpose times lambda 2 v2, I can factor out the lambda since that's a scalar, and I get v1 transpose times v2, or in other words, this is just the dot product between v1 and v2. I already know that's 0, so this is going to be lambda 2 over sigma 1 sigma 2 times 0, which is equal to 0. So that's how we know that U is going to have orthogonal columns. Of course, if we want to normalize it, we just have to scale all of these PIs by 1 over the magnitude of the PI, and then we can normalize those vectors as well. So far everything's good, everything's working out. Now I'm going to start off by writing the equation AV. Okay, so AV. Okay, well, what's that going to consist of? So the A matrix is some set of values that we don't know, right? But V contains the eigenvectors, which are V1, V2. These are all columns. This is just the V matrix, not the V transpose matrix, up to Vn. Yes, Vn. There are going to be n of those. Okay, great. So now what I know is that each of these columns will multiply the A matrix. So I can write this new matrix as AV1, AV2, all the way up to AVN. Now for a moment, let's take a look at the product of U and sigma. U and sigma. And what I want to establish here is that I want to show that AV is equal to U sigma. And the reason I'm going to do that is because V, if it's as long as that's an orthonormal matrix, then it follows that the inverse of V is equal to V transpose. And if that's the case, then if I multiply the left and right by V inverse on the right-hand side of each of those two sides, and I have U sigma times V inverse. Well, since V inverse is equal to V transpose, those give me the identity, and I have that A is equal to U sigma V transpose. But in order to get to that point, I have to show that these two matrices, these two matrix products are equal to one another. Now U sigma, U consists of the PIs, and each of the PIs is equal to A times the VI divided by the sigma I. So that'll be a column. That's really what we're calling, what we often refer to as P1. The next columns will be similar, AV2, that's sigma 1, divided by sigma 2, and that's the next column. That's the P2 column. And this will, of course, go all the way up to the maximum number of these that we will have, which is, we have m of them. So we'll have A, V, M over sigma M. And now this is going to multiply the sigma matrix. I'm going to try to compact in here. This is going to be sigma 1, sigma 2, all the way down to, well, let's see, U. U is an M by M matrix. This one is an M by N matrix. And then we have zeros everywhere else. Okay, so what I will have here in this product is this first column just has a sigma 1 and then zeros all the way down. So this, the columns here will receive the scalars sigma 1, 0, 0, 0, 0, etc. So the first product between this column and the columns of this first matrix will produce sigma 1 times AV1 divided by sigma 1. And so we see that the sigma 1s cancel out, and what I'm left with is AV1, which is exactly the same thing I have over here in AV. Now I could repeat this. I'm going to have, this is going to produce an M by N matrix, so I'm going to have N of these terms until we get down to sigma N multiplied by AVN divided by sigma N. And again, those will cancel, and I've established that AV equals U sigma, which means, by what we've done over here, that A is equal to U sigma V transpose. Now, this is why we let, well, one of the reasons why we divide by sigma 1, because when the sigma matrix multiplies the U matrix, the sigmas cancel and provide us with that nice product A times V1. And so this is just kind of a quick and dirty derivation, or at least a demonstration of why it is the case that A can be decomposed into the product of these three matrices, and why these three matrices are, well, rather why the two matrices U and sigma are defined the way they are. V is as it is because of the fact that it contains the eigenvectors, and then U contains these special combinations of the eigenvectors to ensure that this product works out.